Thanks. Okay, so introduction to graph theory. So today I'm going to cover what I want from sections 10.1 and 10.2 and a little bit from 10.8 because it's related to what I'm going to talk about. The WebWorks, I think, is open right now. Um, Once I've done up to section 10.3, you should have at least all the terminology, maybe not all the material to do the all the questions, but after today you'll be able to do a few questions, and I guess next week you should be fine. Um, okay, so let's just start with some very basic stuff. So what is graph theory? First of all, this, and I've said this before, but just to make sure, this has absolutely nothing to do with graphs, like graphs of functions that you've seen in high school or Cal 1, Cal 2 and such. Okay, so it's the same name, but it's for completely different reasons. These are not related. Um, this is a very, very active branch of mathematics today. I use, so the stuff I'm going to show you, this is stuff that I use in my research every day. I mean, it's like very basic, but it's the language of many of the underlying many of the things that I do. So these are discrete structures. These are finite objects. Although you can consider infinite graphs, that's fine. But we're going to concentrate on um, finite graphs, and it's a very flexible concept that can model a lot of things that are interesting for computer scientists, such as um, in problems like transportation problems. You can also model algorithms, communication networks, and things like that. So it's a very, very, very flexible um, structure object that can be used in many, many, many different kinds of ways. So let's start with some basic definitions. Now, this is not the most exciting part, but at least it's simple. Okay. Unfortunately, to this day, there is no totally 100% uniform agreement on basic definitions. So you will see slight differences from book to book. The concepts are the same, but the names, and there's slight little differences here and there. I mean, once you get used to it a little bit, it's fine. You can see the differences, but just be advised that you may open some book and you say, wait a minute, that's not exactly the same thing that I saw in that other book. This is normal. Okay, so for our purposes, I think I stuck to the definitions that came from the book just to make sure that it was at least uniform in the course. So what we call a graph is a pair of two sets. So there is a set V and a set E. The set V is just a non-empty set, and the elements of this set we call the vertices or nodes of the graph. Okay. And E is a subset of V times V. So it's a bunch of pairs of vertices or nodes, and these are called edges or arcs of the graph G. Okay. So why is this called a graph? Because if the whole thing is small enough, you can draw it and you get a picture, as you can see on this slide. So here is an example of a graph G, a typical example. So the set V consists of 0, 1, 2, 3. So these are the vertices of the graph. And E is the set of pairs 0, 0, 1, 0, 1, 2, 3, 2, and 2, 3, which when you read it like that, sort of meaningless. It's just a bunch of pairs. But when you draw it, suddenly it just has some sort of more intuitive content that we can see what's going on. So you see that I draw an arrow from, let's say, 1 to 0, because 1, 0 is a pair in the set E. I have an arrow from 0 to itself because 0, 0 is a pair in E, and so on and so forth, right? So you can see that from the set E, you can get the picture, and from the picture, you can get back the set E, okay? So as I said, you could, I mean, there's no reason why not considering graphs which are infinite. I have friends who did a lot of papers on infinite graphs, and there's a lot of interesting stuff there. But obviously, from a computer scientist point of view, they are not as common or as interesting. So here we're going to consider only finite graphs. Okay, an edge of the form VV we call a loop, right? So it's a loop. Okay, so the definition I gave you allows loops and directed edges, directed arcs, in the sense that the pair 1, 2 or the pair 2, 1, these are different pairs, right? Sometimes, often, these are called directed graphs or digraphs for short. Okay, this is the terminology that I'm used to. But often we are interested in graphs which have no orientation on the edges and no loops, and they get a special name. They're called simple graphs. So a simple graph is a graph which has just edges between two vertices but no direction, and there are no loops. Okay, so often it is defined, a simple graph is defined as you can see here, but you see there's a slight clash between the previous definition, this one. So you have to say within the context, is this a simple graph or not? Okay. So a simple graph can be defined as follows. So it's a pair VE, where V is a set of vertices or nodes, it's non-empty, and E is a set of pairs of distinct vertices, which we call the edges, but we don't consider these as ordered, and we don't have loops. Okay, so here is a simple graph. Okay, and so I'm giving you the vertex set 0, 1, 2, 3, and the edge set consists of 0, 1, 1, 3, 3, 2, and 1, 2, and I can draw it as I just did. Okay, now if I said this is just a graph without saying it's simple graph, then you might have orientations, but don't worry about that. It's just, I'm just telling you because if it bothers you, it's okay. It's not a big deal. It's just question of context. Okay, it's not deep or important. Now, the same graph can be drawn obviously in many different ways. Okay, this is just a representation to help us visualize or understand the structure, because our vision is a good way of apprehending the universe around us. I'm sorry, this is not a good day. Okay, so here are drawings of the very same graph that I drew on the previous slide. So it's exactly the same graph, but it's just drawn differently, right? Okay, so I think everybody's okay with this. It's very simple. Okay. Multigraphs, I will mention them here and maybe once in a while, but just to let you know that these things exist. A multigraph allows multiple edges between the two same vertices. We're not really going to consider these here, okay? And what we call an undirected graph would be a graph with no orientation on the edges, but we would allow loops. So it's somewhere between very general graphs and simple graphs, somewhere in between. So if you see undirected graph, although again, in some books, papers, somebody might say our graphs are undirected, but they'll tell you they won't have loops. So again, there's these slight differences that you might see here and there. Again, do not worry too much about this. Okay. More terminology. Okay. So let's say I have a graph G, which is an undirected graph, and I have an edge E, which happens to be the pair UV, or U and V are vertices of G. then this is very standard terminology. U and V are said to be adjacent or to be neighbors because there's an edge in between them, right? And if we're talking about the edge, we'll say that it's incident to U and V, okay? If I have a vertex U in a graph, its neighborhood, well, that's the set of its neighbors, and that's denoted N of U. These are all the neighbors of the vertex U, and the degree of a vertex is the number of neighbors that it has, except loops are counted twice. I'm going to show you an example in just a second. I will explain why we count loops twice, okay? So let's see. So U and V are adjacent if there's an edge between them, and this edge is said to be incident to these two vertices. Neighborhood and degree is the number of neighbors, which is neighborhood. Okay, here is an example. So this graph has 1, 2, 3, 4, 5, 6, 7 vertices. 1, 2, 3, 4, 9 edges. Yes. And I have here all the degrees of these vertices, okay? So let's consider, for example, the vertex A. It has degree 2 because it has two neighbors, which are B and F. Again, this is not very deep, right? B has degree 4, right? F has degree 4. The neighbors of F are A, B, C, and E. You can see this directly from the picture. G has no neighbors, so N of G is empty. A vertex with no neighbors, so of degree 0, is called an isolated vertex for obvious reasons, right? So this vertex is isolated. And a vertex of degree 1 is this useful word to have, is a pendant vertex, like it's hanging like that. Okay, so again, this is just terminology. There is absolutely no idea here yet of any depth. Okay, here's an example with loops. Okay, so I have a vertex, I have a graph with 4 vertices. Yeah, the plural of vertex, singular vertex, plural vertices. A, B, C, and D are the vertices. The degrees are as follows. So the degree of A is 2, degree of C is 3, degree of D is 1. That's easy. And degree of B is 4. The reason is that we count the loop twice. And I will explain why we do that, although from a sort of geometric kind of point of view, you might say there's a certain logic to this. Okay, so the neighbors of B are A, B, C. So be careful, right? B is considered to have degree 4, even though it has 3 neighbors. Okay. All right. Our first result, the handshaking lemma. So what does the handshaking lemma say? Nothing very deep, but it's a remarkably useful little observation. So if I take a graph, an undirected graph, so we're allowing loops here, which has M edges, then if you add up all the degrees of all the vertices in the graph, you will get 2M, twice the number of edges. Okay, so a bit of notation. This is fairly standard. So I haven't introduced the sigma notation like this before, but you can guess what this means, right? So this is the sum of all the degrees over what? All the vertices of the graph. So as I wrote here lower, so what I mean by this is you add all the possible degrees of the vertices. Okay, now why is this true? Well, if I count all the degrees of the vertices, I'm going to be counting every edge exactly twice, right? So if let's say I take a vertex, its degree is the number of edges that are incident to it, and I do that for every vertex, think what happens to a single edge. It'll be counted once for one side, it'll be counted a second time for the other vertex, like that. And you see that loops will be counted twice. So that's why we declare the degree to count loops twice for this formula to work. Does this make sense? I wish I could really have a second screen at the same time so I could draw, but if you have the slides close by, you can go back to, or maybe I should go back, go forward or back. I'll go back. Okay, so here if you count all the degrees, right, 2 plus 4 plus 3 plus 1, that's 10. And how many edges are there? 1, 2, 3, 4, 5, right? So you see that when you count the degree of D like that, you're sort of counting this edge once. And then when you count the degree of C, you'll be counting this edge a second time. And you're going to do this for every single edge. Does that make sense?
Yeah.
Yeah.
Yes.
All right.
Yes.
Excellent. Okay. Here is a corollary of the handshaking lemma, which is sometimes useful, but it's more an observation than anything else. It says that an undirected graph has an even number of vertices which have odd degree. So I repeat, if you look at all the vertices in the graph, they either have even degree or odd degree. Those of odd degree, there has to be an even number of these. And why is that? So you take the handshaking lemma, which says that if you add all the degrees together, you get twice the number of edges. Okay. Now split up this sum of all degrees into two parts. There's going to be the sum of the even degrees and the sum of the odd degrees. So you split this sum up in two. So there are three terms in this equality. This is even, the left-hand side is even, so it means that the right-hand side has to be even. Now the sum of even degrees is clearly even. You're adding a bunch of even numbers. So if this is even, it means that the last thing, the sum of the odd degrees, has to be also even. But if I'm adding odd numbers, to get an even number, I have to have an even number of those, right? So that's where this comes from. This would be slightly better on the blackboard, but switching from one to the other is just painful. So I'm afraid you're going to have to, we're going to have to live with this like that, okay? So if you apply the handshaking lemma, you get as a consequence that any graph has an even number of vertices of odd degree. And this can be useful in certain situations. All right. Let's now move to the directed case. So the more general case of what we call digraphs. Okay. So now there's an orientation on the edges. So you might go from 0 to 1, but not from 1 back to 0, or you might have both. So things get a bit more complicated in a sense, or more sophisticated if you want. Okay. So suppose that I have a graph, or digraph G, I should say, and I have an edge or arc E from U to V. Really now it's really from U to V. So U is called the initial vertex of this edge, and V is the end vertex or terminal vertex of the edge. Okay. Why don't like this mouse? Okay. Now now when we had the undirected case, we looked at the degree of a vertex. That's just basically counting all the edges that are incident to it. But now there are edges going out and edges going in, and we'd like to refine this analysis. So we're going to talk about in degree and out degree, and that should be fairly natural if you see what this is doing. So the in degree of a vertex V, and the notation is degree with a minus sign like that, a V, that's the number of arcs which end at V, that go into V, okay? The out degree of V, and this is denoted degree with a plus, that's the number of arcs that go out of V, which have V as initial vertex. Okay, so it's a bit more refined, right? Less rough than just in the case of undirected graphs. So here's an example. So this is a digraph. This is as general as it gets, right? So, and I have 5 vertices, and I look at the in and out degrees of all these vertices. So let's look at A. So A has 1, 2, 3, 4 edges going out, right? 1 to C, 1 to B, 1 to E, and 1 back to A, right? So that's out degree 4. In degree, what goes into A? There's one from E, and there's one from A. So you see in the directed case, the fact that the loop counts twice, it counts once for out degree and once for in degree, is very natural. Okay, so if you were to forget about the orientation, just erase these little arrows and just look at this as an undirected graph. You wanted the degrees, you could just add these numbers together and you'd get the degree. So loops would count twice, right? Is that okay? Does that make sense? Yeah, that's simple. That's very simple, right?
Yeah.
Good, excellent. Okay. Yeah. So here's the handshaking lemma for digraphs, which in fact is even easier than for the undirected case, is that if you add up all the in degrees in the graph, the digraph, I should say, then you get the same as if you added up all the out degrees in the digraph. And that's sort of obvious because whenever you're counting the in degree, you're counting the number of arcs, going in, right? So each arc will get counted once, right? And same thing if you count the, did I say in, out? Anyway, either one, right? So you're counting the arcs exactly once in each sum. Okay, so that's even easier. So maybe I can go back to the previous one here. So if you add up all the in degrees, you get 4, 12 like that, and here 12 also like that, right? Which is, notice, exactly the number of arcs: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So that's, I mean, it's even simpler than the undirected case in a sense. It's an almost trivial observation. Okay, all right. Now I'm going to show you some basic toys, basic graphs to play with. Very, very, very basic. The most natural, simplest examples we can think of. The first family of graphs, these are the complete graphs. As their name tells you, they're complete in the sense that every possible edge is there. They are simple graphs, though. There are no loops, no orientation, but otherwise every possible edge is present. So formally, so let's call that Kn for every n greater or equal to 1. The vertices are the numbers from 1 to n. And what are the edges? Every single pair of vertices other than no loops, right? So K1 is just a vertex, K2, 2 vertices and the edge between, K3 is a triangle, every possible edge, K4, every possible, you see. So you have infinitely many of these graphs. These are the complete graphs. So they're sort of stupid, right? In the sense that they're just like, they don't seem to be very interesting, but in a sense, they are very, very, very important. Okay. So these are the complete graphs. The cycles, also very natural, very simple. So Cn will denote the cycle of length n. N is at least 3. Okay. So the vertices are 0 to n minus 1. And what are the edges? 0 to 1, 1 to 2, right up back to 0, right? So C3 is the triangle. Notice that it's the same as K3. K3 and C3 are the same, okay? C4, 4 cycle, C5, 5 cycle, C6, 6 cycle, and so on. These are the cycles. Yeah. The wheels. So you take a cycle and you put a new vertex. I'm going to say in the middle, but you don't, I mean, I drew them this way because that's the simplest way to draw them, but you can draw them in many other ways. But think of it, so that's why they're called wheels, right? So you take a cycle, you add a vertex in the middle, and it's adjacent to every vertex in the cycle. Okay, so this is called a universal vertex. This is a general concept. A vertex is universal so if it's adjacent to every vertex in the graph. Okay, so W3, the three wheel, you take a 3 cycle and you have this vertex, let's say U, which is adjacent to everybody here. W4, so the 4 cycle plus a vertex adjacent to everybody. And you see why they're called wheels. Yeah, yes. Okay, so far so good. This is simple. That's good. Okay, hypercubes. Not quite as simple. Okay, so n is a positive integer. We're going to define the n-dimensional hypercube that we will denote by Qn. So its vertices are all bit strings of length n. Okay. And you take two strings like this, and they will be adjacent if they are exactly the same except in one bit. Okay, so two bit strings will be adjacent. There'll be an edge between them if they differ in exactly one position. So if you look at, for example, here 0, 0, 0 is adjacent. So that would be in the three-dimensional hypercube. 0, 0, 0 will be adjacent exactly to 0, 0, 1. 0, 1, 0.
Hello.
Welcome back.
You're muted, sir, by the way.
Yeah, I don't know what happened. That's the first time in more than a year. Okay, let's see what's going on. So I guess I have to share again. It's been, I think the whole thing, I don't know if it kept recording, but I just lost you guys. Everybody just disappeared. Is everybody?
Well, it says recording in the top left corner, so I think
Yeah.
it never stopped.
All right. Yeah, you can hear me? Yeah, okay.
We hear you.
Yep.
No, you're
Yeah, it's
all
all
good.
Okay. All right. So I don't know at what point you lost this whole thing, but did I give you the definition of hypercube?
I think you should start hypercubes again. I don't know where it cut off for anybody else.
All right. Okay, so let's do that again. Taking positive integer n, we're going to define for each n something called the n-dimensional hypercube, denoted by Qn. So what are its vertices? Its vertices are, sorry, I want this here. Okay, so the vertices are the bit strings of length n. Okay, and so when you define a graph, you have to say what the vertices are, and you have to say when two vertices are adjacent or not. So here, two vertices, which are two bit strings of length n, when are they adjacent? If they differ in exactly one bit. So they're exactly the same except in one position, okay? So in the three-dimensional hypercube, if you look at 0, 0, 0, this is a vertex. It is adjacent precisely to 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And 101 is not adjacent to 110. You see that these differ in 2 bits. The last 2 bits are different, so they're not adjacent. So
Would it be adjacent to 001?
Yes, 101 is adjacent to 001. Yes, absolutely. Yeah. So let me show you the first few hypercubes. So Q1, let me try something. Does this make a difference? I'll bet you don't see any difference, but for me it's better. Okay.
I don't see much difference, no?
I mean, you see the slides? Yeah?
Yeah, we see the slides.
Good. Okay. All right. Because it says sharing is pause, bring your shared window. But you see, okay. Oh. Yeah, everybody sees the slide, sorry. Okay, so
Yeah,
Q1.
this is fine.
Yeah.
Well, we're on 10.2. I think it's not changing slides.
Okay, this is annoying. Now,
Yeah, now it's changing.
so Q1, this is the one-dimensional hypercube, bit strings of length 1, so that's 0 and 1, and they are adjacent because they differ in exactly one place. Q2, bit strings of length 2, and it's easy to see that this is the hypercube, two-dimensional hypercube. This is the three-dimensional hypercube, like that. And I'll let you draw the four-dimensional hypercube, but there's a nice little way of doing this. If you think about it a little bit, it makes sense. So you can create the next hypercube from the previous one as follows. So if you look here at Q1, okay, so you have these 2 bits, 0 and 1. You want to create Q2 from that. So basically what you're going to do is, so look at this edge here, 0, 0, 1, 0. Okay, it's the same as this, except that you added a 0 to both bits, right? And this is another copy where you added a 1 to both these bits, right? So in other words, you take this Q1, you make 2 copies of it, and you connect the copies in the obvious way like that. So there's the 0 copy and there's the 1 copy, and you just connect them like that, okay? Now, if you want to go from Q2 to Q3, what do? You have, let's say, the 0 copy of this, which would be the left face here, and the 1 copy would be the right face here. So now you have 2 copies of Q2, and you connect them in the obvious way, like that. So now you can guess what Q4 looks like, a 4-dimensional hypercube. You'll make a second copy of this. You'll have this is the 0 copy. You'll have the 1 copy, and you will connect corresponding vertices like that. You're going in the 4th dimension like that. And then you can create the 5-dimensional hypercube like that, but it gets a little messy, obviously. But that's a nice little exercise. Okay, bipartite graphs, what time is it? Okay, good. So let's say bipartite graph. So we'll say that, so a simple graph here, no loops, no orientation. Bipartite graphs like super important for algorithms. And I'll try to explain a little bit why in just a few minutes. So a simple graph is bipartite if it has the following property. You can partition the vertex set into 2 pieces. So you can cut the vertex set as a disjoint union of 2 sets, let's say V1 and V2, such that the edges are never inside V1 or V2, but across. They have to go from V1 to V2. Okay, there's no orientation, but they connect a vertex in V1 and a vertex in V2. Okay, so here's an example, C6, the 6th cycle, is bipartite. You see that I drew the cycle in a sort of unusual way, right? The natural way would be just to draw a cycle like that, but it's, for my purposes here, it is more convenient to draw it as I did, because now I look at the even numbered vertices 0, 2, and 4, and I look at the odd numbered vertices 1, 3, 5, and you see that the edges are all across, right? So every edge connects a vertex in one piece to a vertex in the other piece. So it is bipartite, okay? All right. So I just repeated the same definition here. So K2, the complete graph on two vertices, is obviously bipartite, right? It's just, there's one edge. But if you look at the complete graph on three vertices or more, it is obviously not bipartite, because if you cut up into two pieces, one of the pieces will contain at least two vertices, right? Pigeonhole principle, yes. So there's one piece that contains at least two vertices, and since it's a complete graph, there's an edge between these two vertices, and that edge does not connect vertices into different pieces, okay? So K2 is bipartite, K1 is bipartite in a trivial way. Yeah, I should, Okay, so a one vertex, as defined, a one vertex graph is not bipartite, which is not a good thing, but it's not a big deal. But anyway, let's just forget about that. Anyway, so K2 is bipartite, K3, K4, K5, none of them are bipartite. Okay. Here's a little observation. It's just a rephrasing of the definition. So I'm saying that a graph is bipartite precisely if I can color the vertices using two colors, such that if you have an edge, the two vertices incident to that edge, or the who's such that the edges incident to those vertices, they get different colors. Okay, this is just a reformulation of the definition. Okay, the blocks, the partition, these two blocks are the colors. Okay, so it means that bipartite graphs are those graphs that can be two colored. And I will go, this little incursion I want to make into 10.8 about graph coloring has to do with coloring graphs with more than two colors. Okay, so bipartite graphs are exactly those graphs that can be two colored. Okay. Before I go back to that, let's define another family of important basic graphs. These are the complete bipartite graphs. Be careful, they're not complete graphs. They are complete bipartite. So they are the bipartite graphs that have the most edges, in a sense. Okay. So now I need two integers, positive m and n, and my graph is called KMN. And it is the complete bipartite graph. What are its vertices? A set with m elements and a set with n elements, like you can see from the picture. And what are the edges? All the edges in between these two sets. Okay, so again, these are the fattest bipartite graphs that you can imagine. So you have two pieces and you put all the edges possible in between. Okay, so K32, for example, I have three vertices on one side, two vertices on the other, and all the edges connecting these two pieces. So it's obviously bipartite, and it has the most edges you can, because if you add an edge in there, you're going to destroy the fact that it's bipartite. Although that's almost obvious. But okay. Yeah. Is that okay?
Yep.
Yes, good. There's a weird echo when you guys are, which wasn't there before. I don't know. Anyway. Yeah, okay. So algorithmics a little bit here. I want I'm interested in recognizing bipartite graphs. So a typical algorithmic job can be, I mean, this is one of the reasons graphs are so, they're very, very, very flexible, is that you can model a lot of algorithmic problems using them. So a typical problem is I'm going to give you a certain property of graphs, and I'm going to ask you to write an algorithm that says if yes or no, a given graph as input has this property or not. So I'm going to give you a graph with like 100 million vertices and like millions and millions of edges. And you have to tell me, is this graph blah, blah, blah. For example, is it bipartite? Okay. Is this easy or not? It turns out that figuring out if a graph is bipartite can be done very, very efficiently. Okay, even for extremely large graphs, you can do this very, very fast. Okay, so I'm not going to show you why it works right now, but I'm going to show you how it works. Okay, but not why it works. Okay, and the trick is this. It's the simplest algorithm you can imagine. So if the graph is bipartite, it means I can color the vertices with two colors such that the edges never connect two vertices of the same color. Okay, so what I can try to do is to actually do the coloring. And so let's say I color, I mean, this, I should redo these slides, but anyway, so this vertex is colored red, okay? I just grab one of the vertices. I mean, the actual color is irrelevant, right? But it'll have to get a color. So let's say it's red, okay? Once I know this vertex is red, then I know that all its neighbors have to be the other color, right? So they will have to be blue. There is absolutely no other choice, okay? Now, the neighbors of these blue vertices, they all have to be red. There is no choice. So they are red. And now the neighbors of all these red vertices have to be blue. And we're lucky because we didn't get a collision. There was no contradiction, okay? And there you go. This graph is bipartite. It's all good, okay? So there was no crash, and this is our coloring, and that's it, okay? So that's really a very simple-minded algorithm, and it turns out that it always works. It can't go wrong. Okay. Now, let's say that I ask you now a slightly different question, which is, could you do this with three colors? Let's say you have red, blue, and green, and I give you this big, big graph, and I say, are you able to color this big, big graph with three colors? So again, the rule is the same. Edges must get different colors on both vertices. That's the only requirement. Okay. Now, with two colors, it's really simple. With three colors, it is really hard, or we think it is. It's as hard as possible. So this greedy way of coloring is not going to work because you might fail, but still it would get it wrong. So here's a little, just to think about this. If you think about this example, you can actually color this graph with three colors is doable, okay? But if you try the same kind of algorithm that we did with two colors, it might not give you the right answer. So, I mean, okay, this is not super important at this point. I just wanted to point that out, but you're starting with this red vertex on the left. And let's say you start with the same trick. You say, okay, its neighbors have to be green or blue, right? And obviously it'll force those two, let's say, whether it's blue, green, you see that these three neighbors, it'll be forced, right? You're only using three colors. The two opposite ones have to be, let's say, blue, and the other one has to be green. Now, if I try to be greedy and then I move to the next, that's where I wrote greedy both ways, right? If you then move on to those and you color those red to be as greedy as possible, right? In the sense that you try to use as the least number of colors as possible, then you will get a no answer with this method. So you'll be stuck with a vertex that cannot get any of the three colors, but it's just that you started wrong. Okay, so you have to backtrack, and it's believed to be basically that there is no way to do this other than by backtracking. But if you can prove it, you'll be a millionaire and you'll get a really good job. Okay. So now I'm going to jump to 10.8 to discuss this a little bit more in detail. So strangely enough, this came from a puzzle that I think I will have time to talk about, which has to do with coloring maps. So in the 19th century, so if you have a map with countries, right, to read this map, to make it easier to read, you'd like to assign different colors to countries which have a common border, right? So it'll make the map easier to read. And somebody at some point asked, oh, but when you have these maps, can you always just use 4 colors and it will always work? And it was like, it took like 150 years to answer the question. And this is the origin of these coloring problems, but they turn out to be much more universal than just coloring maps. Okay, so let's define what a coloring is. So I have a simple graph. So no orientation, no loops. A vertex, because there's also stuff which are edge colorings, but here when I talk about colorings, I mean a proper vertex coloring. I mean, you assign colors to the vertices of your graph such that if 2 vertices are adjacent, they must get different colors. Okay. So if G has a coloring with K colors, a proper coloring with K colors, we say that it is K colorable. Obviously, if you have lots of colors, you can always do it. The question is, how many you want to use as few colors as possible to do it. Okay, so question, I give you a graph and I ask you, what is the least number of colors that you can use to color it? And this turns out to be a very, very difficult question. Okay, so this number is called the chromatic number of a graph, and the notation is chi of G. Chi is a Greek letter. So this is the least number of colors that you can use for that particular graph. Here are some examples. So the graph K2, the edge, it requires 2 colors. Obviously, you don't need more. Okay. K3, the triangle, you clearly need 3 colors to color it, right? You need a different color for each vertex. What about this guy? Well, you can see that you can repeat that color over here, right? So if this is blue, red, green, you can reuse blue here and you'll be fine. So 3 colors will be enough. The 5 cycle, you can try these by yourselves, right? I'm not actually doing the computations here, but they're very, very simple. The 5 cycle, 3 colors will be necessary and sufficient. Hypercubes in general, I'll talk about it on the next slide, but all the hypercubes are bipartite. 2 colors will suffice. Complete graph on 4 vertices, 4. And in general, you can see that the complete graph on n vertices will require as many colors as there are vertices because everybody's adjacent to everybody else. So you can't save on colors. The cycles, if the cycle is of even length, you can just alternate colors, blue, green, blue, green, blue, green, blue, green. You'll come back and everything is fine. But if it's odd, you'll get stuck at some point, right? When you cycle back up, think of the 5 cycle, blue, green, you need a 3rd color. This is true for any odd cycle. For the wheels, it's exactly the same thing, except you need an extra color for the middle of the wheel, right? Have I lost everybody? Are you just like watching cartoons on something else, or is this not too bad?
That's fine.
It makes
Yeah.
sense.
Speak again. I know what's going on. For some, what?
Hello, test 1, 2.
Yeah, okay. It's because something went wrong with my computer. Okay, so usually the sound card I use cuts off the speakers on my Mac. So now I've got like, okay, I see what's going on. Something very strange happened. Okay, chromatic number. So exercise, prove that the hypercubes are two colorable. So basically you want to provide a two coloring of any hypercube. The hint is that there's a very, very simple, cute way to determine the color you should give to a bit string. Okay, so if you think about it a few minutes, you'll figure it out. And yes, okay, so here I wrote a graph G is bipartite if and only if its chromatic number is at most 2, because I've included the one element graph, but you could write it equal to, but it doesn't matter. Yeah, so what I was trying to say earlier, or what I was saying not so clearly, is that bipartite graphs, recognizing bipartite graphs is efficient. There's a very simple, very efficient algorithm to recognize bipartite graphs. But so is G2 colorable? That's an easy problem. But is G3 colorable? That's NP complete. That's as hard as all those problems I was talking about during the whole semester, and I should actually take some time to go into this into a bit more detail. But so again, if you find an efficient algorithm to determine if a graph is 3 colorable, you will be rich and famous, or in jail, depending on how you choose to use this algorithm. Yeah, so starting at 3, it becomes an NP complete problem, so as hard as we think it can be. Yeah. Okay, and finally, I'm gonna stop after this slide. This is stuff that I've added because in the WebWorks these are used. So this terminology is used. So the order of a graph, that's just the number of vertices. That's a standard name for the number of vertices. You will see that. The degree sequence of a graph, what is that? You just list the degrees of the vertices of the graph in non-increasing order. So from big to small, if you wish, okay? So the degree sequence of the 4 cycle is 2, 2, 2, 2, because everybody has degree. It's a cycle. Everybody has degree 2. The wheel, W4, remember this is the cycle, 4 cycle, and you add somebody in the middle. This guy in the middle has degree 4. So that's its degree here. And then everybody else has degree 3, which is 2 for the cycle and 1 for the new vertex. Okay. The degree sequence of the simple graph illustrated earlier is 3, 2, 2, 1. I can go back if you wish. And the degree sequence of the graph we used earlier to illustrate the notion of degree in neighborhoods is 4, 4, 4, 3, 2, 1, 0. So you can go take a look at these examples later. Okay, so that's all the degree sequence is. So there are a couple of questions that deal with the degree sequence of graphs. So I just wanted to add that in so you have that information. Are there, and that's what I wanted to do today. So it's mostly definitions, right? I didn't prove anything very deep here. Any questions, comments?
Could you go back to the definition of the complete bipartite graph?
Yes.
The same I didn't quite get there.
Oop, right here. Yep.
So what do you mean the disjoint union?
Yeah.
Is that like the XOR? Or?
Yeah. Sorry. I mean, you take two. I just mean that you take the two sets which are disjoint, and you take their union. They have nothing in common. It's because I actually didn't name the elements. I think I did this to avoid too much notation. But let's say you could call the vertices on one side, you could call them A1 to AN, and the other ones on the other side, you could call them B1 to BM.
Okay.
Do you see what I mean? It just means I take two sets which don't have anything in common. I don't want these two sets to have anything in common, and I put all the edges in between them. That's all.
Okay.
There's nothing hidden deep or anything.
Okay.
Other questions? No? Okay, so on Monday, I will continue with section 10.3. And again, you don't have all that is required for doing the webworks, but you could probably start doing some problem, but probably not that many. But if you want, you can try it. But you don't know everything that you need to know. All right. Goodbye.
Goodbye.
Bye.
Thank you.
Thank you.
Thank you. Goodbye.
Bye.